What if the most promising place to find life in our entire solar system is not Mars, not Europa, not Enceladus, but a mysterious frozen world orbiting the most distant giant planet we know? What if, beneath a crust so brutally cold it could shatter steel, there is an ocean, vast, ancient, completely sealed off from the sun for billions of years? And what if that ocean isn't empty? Today we're diving into one of the most unsettling possibilities in modern planetary science. Could Triton's hidden ocean be hiding life? It all began when researchers studying the thermal history of Neptune's largest moon noticed something impossible. Triton should be geologically dead, a frozen, locked-down ice sphere drifting through the edge of darkness. But instead, it behaves like a living world. Its surface is smooth, young, constantly reshaped. Its crust shows signs of stretching and melting, and towering geysers, some erupting higher than Mount Everest, have been seen blasting into the void. Those geysers changed everything. Because if something is active beneath the ice, then something is transferring heat upward. And heat, in a place this cold, can only come from one of two sources: geological processes or biological ones. But before we even approach the possibility of life, we need to understand the monster we're dealing with. Triton is one of the coldest objects ever observed, sitting at minus 235 degrees Celsius. Its nitrogen surface is so frigid it behaves like a rock. Its atmosphere is razor-thin. Its orbit is retrograde, meaning it moves the wrong direction around Neptune, like it was captured from deep space long ago. That capture event may have torn Triton apart internally, melting the entire moon and creating a global subsurface ocean that has been trapped ever since. That ocean, according to recent thermal and gravitational models, could be over 100 kilometers deep, more water than all of Earth's oceans combined, inside a world drifting 4.5 billion kilometers from the sun. But the most intriguing mystery came from the distribution of heat beneath Triton's crust. Some regions showed warm pockets that shifted slightly over time. The movement wasn't random. It had a pattern, almost like a slow pulse. And that pulse raised a terrifying question. Is something beneath Triton's ice generating heat on purpose? To unravel this mystery, scientists looked at Earth. Not at our forests or our rainforests, but at the pitch-black trenches of our deep oceans. Down there, sunlight never reaches. Pressures are crushing. Temperatures hover near freezing. And yet, life thrives. Entire ecosystems grow around hydrothermal vents powered not by sunlight, but by chemistry. Life fueled by heat and minerals erupting from the planetary crust. And the more researchers studied those vent ecosystems, the more one realization became unavoidable. If life can emerge in the deepest, darkest corners of Earth, then Triton's ocean might be even more suitable than we thought. Because unlike Europa or Enceladus, which rely mostly on tidal heating, Triton may have an additional energy source: radioactive decay within its rocky core. Combine that with salts in the water, and you get a stable environment capable of powering chemical reactions for billions of years. That is more than enough time for life to develop. But here's where the mystery deepens. Under Triton's surface, models show heat spreading in branching paths, as if guided by channels, not just convection. And in several simulations, those paths appear to follow fractures in the ice. Something is flowing, or moving, or clustering along those fractures. But life, if it exists there, would be nothing like the organisms we know. Without sunlight, without oxygen, without stable surfaces, it would likely be microscopic. Chemical-driven colonies metabolizing hydrogen, methane, nitrogen, or sulfides. Think of organisms that resemble living mineral formations more than animals. Life that grows as webs, films, or networks, migrating toward chemical gradients and leaving heat signatures behind. This idea isn't science fiction. On Earth, microbial mats shift and migrate.
Slime molds navigate mazes. Even single-celled organisms can collectively react to stimuli in ways that look eerily coordinated. So when Triton's thermal signatures showed slow lateral movement lasting months, it sparked a quiet but profound debate. Are we seeing groundwater circulation? Cryovolcanic buildup? Or is this the first indirect evidence of an active biological network beneath the ice? The possibility wasn't dismissed, it was feared. Because living systems beneath Triton's crust wouldn't just survive, they could evolve in total isolation, forming biochemistries unlike anything in the solar system.
But the biggest clue doesn't come from heat signatures. It comes from Triton's sky. Since Voyager 2's flyby, scientists have noticed something deeply puzzling about the Moon's thin atmosphere. It contains nitrogen, methane, and trace organics. But those organics shouldn't last. Triton's atmosphere is constantly stripped away by solar radiation, yet somehow it keeps getting replenished. So where is the new material coming from? The obvious answer is cryovolcanism, icy volcanoes blasting material upward from the interior. But there's a twist. Some of the organic compounds detected resemble complex carbon chains far more elaborate than what saltwater and rock alone should produce. That doesn't prove life, but it adds weight to the idea that something inside Triton is actively generating organic molecules. And then there are the geysers themselves. They erupt in precise clusters, they appear seasonally, and their plumes rise higher than any other cryovolcanic jets in the solar system. This suggests pressure, not random melting, is driving them. Pressure from expanding gas, pressure from chemical reactions, pressure that might be influenced by something shifting beneath the ice. But here's the part mainstream science rarely discusses publicly. The geometry of the plumes matches the stress lines where models predict the ocean comes closest to the surface. And if organisms exist in those water layers, they could be periodically ejected into space, microscopic, frozen, dormant, yet detectable. Several teams are now reanalyzing Voyager's data, searching for any overlooked organic signatures in those plume particles. But the most provocative hypothesis is something entirely new, that Triton's ocean might host networked biochemistry, not life as individual organisms, but life behaving like a system. Imagine a web of microscopic entities interacting chemically and thermally across massive distances, a distributed, collective life form evolving in a world of darkness and pressure. If such a system exists, then the thermal pulses detected could be its signature, a slow shift of metabolic activity across the ocean floor, a biological tide. And if that tide is strong enough, it might subtly reshape the crust above, triggering stress fractures and geysers. Imagine that. Not only hidden life, but life influencing the geology of an entire moon. So could Triton's hidden ocean be hiding life? Let's put the clues together. We have a captured Kuiper Belt object likely formed far from the sun, rich in organic compounds from the start. We have tidal heating, radioactive decay, and salt-rich water capable of sustaining stable chemical cycles for billions of years. We have shifting thermal anomalies beneath the crust, behaving like slowly migrating heat signatures. We have plumes releasing material that shouldn't exist unless something deep below is producing it. And we have an atmosphere continually replenished with complex organics. All of this forms a picture that is difficult to ignore. Triton isn't dead. Triton isn't silent. Triton may be one of the most biologically active locations in the entire outer solar system. But the final twist is the most shocking of all. If life exists beneath Triton's ice, it may predate Earth's biosphere. It may come from the same primordial chemistry that once filled the early Kuiper Belt. And if Triton really was captured by Neptune, that means life, if present, has survived a violent gravitational event, tidal heating, freezing, pressure, darkness, and complete isolation. That would make it the toughest, oldest, and most alien life in the solar system. And here's the true cosmic implication. If life evolved independently on Triton, in an environment this extreme, then life in the universe must be common. Not rare, not fragile, not exceptional. Common, resilient, inevitable. So the question isn't, does Triton's ocean hide life? The real question is, what will humanity discover when we finally send a probe through those geysers? What will we find frozen into those nitrogen particles drifting through space? Will we see the first undeniable signatures of extraterrestrial biology, proof that we are not alone? Or will Triton reveal something even stranger, something that forces us to rethink not just what life is, but where it can exist? Until we launch a mission, we won't know. But one thing is certain. If there is a second genesis of life in our solar system, if there is a hidden ecosystem older than Earth itself, Triton is where it's hiding. And whatever waits in that ancient ocean might rewrite everything we thought we understood about life in the universe.